Problem statement: diabetes is a serious global health issue that is often diagnosed too late, leading to complications and high treatment costs. A data-driven approach is needed to identify high-risk individuals yearly using commonly available health data.
Now, the select objectives. First, to develop classification model that can predict diabetes based on clinical data. 2. To compare the performance of different classification algorithms using a prototype and an evolution metric. 3. To analyze and interpret model results to determine their suitability for diabetes prediction. 4. To demonstrate the application of data analytic technique using orange data mimic.
The dataset contains 768 patient records with a total of 9 attributes. These attributes represent medical and demographic information. They are commonly used to assess the risk of diabetes. The input features include number of pregnancies, glucose level, blood pressure, skin thickness, insulin level, body mass index or BMI, diabetes predictive function, and age. Each of these features provide important information related to patients' health conditions and potential risk factor for diabetes. For example, glucose level is a key indicator of diabetes, while BMI reflects body fat level that may influence insulin resistance. The diabetes predictive function represents genetic influence, and age is included because the risk of diabetes generally increases as people get older. The target variable in this dataset is called outcome, where a value of 1 indicates a diabetic patient and 0 indicates a non-diabetic patient. This makes the problem a binary classification task, where the goal is to predict whether a patient is diabetic or not based on given features.
Assalamualaikum. I will present about introduction. Diabetes is major global and national health challenge. 1 million affected worldwide and nearly 1 in 5 adults in Malaysia diagnosis. Late detection often lead to several complications and higher treatment costs. AI and machine learning offer a powerful solution by analyzing health data to predict diabetes risk early, enabling timely intervention and helping prevent complications. This project developed a simple and effective tool to identify at-risk patients, supporting yearly screening and better healthcare outcome.
In this section, I will explain the methodology used in this diabetes classification project. First, I will start with the classification approach. In this project, a classification approach was chosen because the main objective is to predict a categorical outcome, whether a patient has diabetes or not. This type of outcome involves discrete class labels, which makes classification more suitable than regression. Regression is normally used to predict continuous values, while medical diagnosis often requires clear category-based decisions. Classification techniques are widely used in healthcare analytics because they help convert complex medical data into meaningful predictions. In this study, the binary classification of diabetic and non-diabetic patients allow healthcare professionals to identify individuals who may be at higher risk. This supports yearly screening and preventive healthcare, where yearly detection can improve treatment outcomes. In addition, classification models provide structure and interpretable outputs that support decision making. By comparing different models, we can evaluate which technique performs better for medical dataset with similar characteristics. The entire workflow, including processing, model training, and evaluation, was implemented using orange data mining and is illustrated in Figure 1. Next, I will discuss the model selection rationale. To ensure a comprehensive evaluation, 4 different classification models were selected and compared. Using multiple models allow us to assess different algorithmic strengths and weakness rather than relying on a single method. The first model is the decision tree. Decision trees are easy to understand because they represent decision logic in a tree-like structure. This is important in clinical settings where healthcare professionals prefer clear and visual explanations. Decision trees can also capture non-linear relationships between variables. However, they are prone to overfitting, which is why they must be evaluated alongside other models. The second model is random forest. Random forest is an assembled method that combines multiple decision trees to improve prediction accuracy and reduce overfitting. This model was chosen because the medical data often contains complex interactions between variables. Random forest also provides feature importance, which helps identify key health indicators related to diabetes. The third model is Support Vector Machine or SVM. SVM was selected because it can handle non-linear decision boundaries using kernel functions. It is effective for datasets with overlapping classes and high-dimensional features. Although it is less interpretable, its strong generalization ability makes it useful for performance comparison. The final model is Logistic Regression. Logistic regression was used as a baseline model due to its simplicity and interpretability. It is commonly used in medical research because its coefficients clearly show how input features affect the probability of diabetes. It also serves as a reliable benchmark for comparing more complex models. Moving on to the data preprocessing. Before training the models, data preprocessing was performed to improve data quality. Several attributes such as glucose, blood pressure, skin thickness, and insulin contain zero values that are not medically realistic. These values were treated as a missing value. Preprocessing was carried out using the preprocess widget in orange. The main step included handling missing values and standardizing numerical features. Standardization ensures that all features are on the same scale, which is especially important for models like logistic regression and SVM. This prevents variables with larger range from dominating the learning process. Finally, I will explain the train test split. The dataset was divided into 70% for training and 30% for testing. This allows the model to be evaluated on unseen data, ensuring a fair assessment of performance. Using a fixed split also supports reproducibility and provides a good balance between training and testing data. That concludes the methodology section. Thank you.
Okay, next is tools. This study uses orange data mining to perform the full analysis. It features vehicles-based workflow, machine learning processes, transparent, interactive, and easy to understand. Distribution plot show clear difference in glucose and BMI between diabetic and non-diabetic patients. Diabetic patients had higher glucose level, confirming glucose as key indicator of diabetes. Next, we move to exploratory data analysis. Data. Distribution plot show the variance in age and insulin level, indicating interaction between multiple risk factors. Correlation analysis confirmed glucose as the strongest predictor, followed by BMI and age. This result validate the use of multivariate models and show that the dataset contain meaningful features for prediction. So for model evaluation metric, we have classification accuracy, CSD, F1 score, precision, praise, and recall. Each metric evaluate model performance from a different angle. Accuracy show overall correctness. Precision measure prediction reliability. Recall is critical to reduce missed cases. And F1 score balance precision and recall. Using multiple metric give a more reliable evaluation of the model.
Models were compared using accuracy, precision, recall, and F1 score. All models perform reasonably well. Logistic regression and SVM show balanced performance. Decision tree had high recall and random forest was competitive. Recall was prioritized to reduce missed diabetes cases, showing the need to select models based on medical priorities, not accuracy alone. The confusion metric was used to analyze the model's performance in more detail. It explains the number of true positive, false positive, true negative, and false negative, providing a clearer evaluation beyond overall accuracy. Based on the result, logistic regression demonstrates balanced performance in predicting both diabetic and non-diabetic cases. This indicates that the model does not favor one class over the other. Importantly, the model produced a low number of false negatives, which is critical in medical screening. Reducing false negative had prevented missed diabetes diagnosis, ensuring the high-risk patient can receive early medical attention. Although random forest and support vector machine models achieved similar performance level, logistic regression was selected due to its better interpretability and more consistent result across the evaluation metrics.
Conclusion. This project applied data analytics and classification technique to predict diabetes using medical data. The results show the glucose, BMI, and age are key risk factors, with logistic regression selected as the best model due its balanced performance and interpretability. Why not a replacement for clinical diagnosis? To model demonstrated strong prediction as a transparent decision support tool for early diabetes screening.